Lab 8, Freefall motion and determine G, the gravitational acceleration. This lab, we analyze the motion of a freefall object, anything that you drop in the air. Okay, we will obtain its motion diagram, which is just dots at the location where this object is. We do this with assistance of a capstone tool. From the data generated, we model the motion with the mathematical functions y as a function of time, which means vertical position with a function of time, and velocity, vertical velocity with a function of time, and record them in the tables. From the graph, we use quadratic linear fit and linear fit to get these two functions automatically. That's what this tool is for, to get the quadratic fit or linear fit for these functions, or get a formula for these functions. And the gravitational acceleration G can then be extracted from these equations. Alright, so here is the background we got from the class. A one-dimensional accelerated motion, that's what a gravity freefall object is, with speeding up or slowing down, and its displacement versus time function is a quadratic equation, which means this equation covers both moving up or moving down, accelerating and deacceleration, with the parameter be positive and negative. And so this A here could be positive and accelerating, and negative deaccelerating, or depending on its sign, contrast to this initial velocity V, and could be positive, negative, relative to the direction chosen, and also this is the initial position. So here acceleration with a unit per meter per second square, it could be implied as speeding up or slowing down, depending on the positive or depending on whether it's positive or negative. The graph of accelerated motion is usually a parabolic curve. Okay, in case of a free-falling object, the displacement versus time function becomes this. So you see, this is just this form. Okay, whether you use x or y as your choice. In this case, we choose y and half, then g and t square, and initial velocity, and this case with 0 and t. And we get this graph for this one. We can get a graph for this one. And then when we calculate one, we use the mathematical tool to fit it. But in general, it use like t equal a t squared bt and the c. You remember in your algebra class, the quadratic function a x squared b x and t and c. And here, and this x is replaced by the t. And so on, but A, B, C are still the same. Okay, and then we compare this equation and this equation. Recognize this A, which is given by the software, is nothing but this half g, and also the B, which will be given, and also is their initial velocity, and C is none other than just the initial position. So you compare it to recognize that's what I'm saying. And B is the initial velocity, C is the initial position. And then obviously, so G is half G, and then 2, you move the 2 to the other side, half G is simply equal to 2A. So now, okay, having said that, let's do exactly, but the ultimate result, you get all this, your plot, and replace yours with your own video. Okay, this is just example. All right, so first step is to load your freefall object video, which I believe you already have, and create the motion diagram object, and by tracing through motion point by point. For this first step, load your freefall video to the capstone and create the motion diagram, which is just simply we call it tracing. So what do? You start on your computer this software. capstone, Pascal capstone. It will take time to start. So now here we go, and forget about these. And then here you start video analysis and looking for the video. Okay, and in my case it's lab 8. That I just use this example. Terran helped me doing that, and then open. It opens. So this completes the first step. You loaded it, this, and then you see. Let me bring back the lab. So I just got to follow step by step. So we're gonna do a motion diagram. So but with motion diagram, you have to know the size or the scale. What do you actually do? You have to use this tool to see this clamp with tip on either side, and so I know the size of this window frame is 1 meter. Okay, and basically I use a meter stick to measure, but somehow very nice number. But in your case, you have to know either a person's height or some object in there. So that is 1 meter. So you tell it 1 meter. So now then you have to have your coordinate. So I will move the coordinates. This coordinate axis I will put on. I don't want to put in here. I don't put on here. If you put here, would be nice, but it's not it. Don't get into trash can. But here, I'll put in here. So clear out the path of this run thing. So therefore, you will see that the ball will start something like 1 meter, 2 meter, and almost 2 meter above the ground, and then it will be negative in x direction. But x direction and horizontal direction is not what we don't really care that much. Basically, it is still. And once you have that, you are ready to get a video game. Down on the right is actually see horizontal. You can put x coordinates basically stay the same, but the y coordinate, and then it will click every time you click. So now once you have that, you choose above here, and that's the tracer. Once you see this turn into a cross, and then you don't want to randomly click other than so once you start tracing, and that what you then put over here and click, you see there is a cross, which means, and then actually it moves. But okay, but the video has a lot of stable. Then you have a lot of things here, but that's actually motion grabber. But and that's not correct, because the video has a lot of pause and nothing interesting. So then I clear out all this. I'll restart, and then you will actually advance. So then you can say go back. Everything will be gone, and then you advance this to certain point. All right, and I have to start over. Now I can clear out the point and start by clicking this, delete all points, and then you restart by forwarding until this left hand. Okay, start from there would be good. All right, in your case, because otherwise it's gonna be boring. It's not moving. So now here start. It's actually has already start some initial velocity. Go. So that's there, and then that's there. But you see down here the time is that means 0.66 seconds. It was here, and then here, and this process is very fast. Just be patient. So this is called a motion diagram. Okay, which means at equal interval time, which means the movie plays one frame, and then every time in this frame you check the position where the object of interest is. So you boom, and hopefully it will not drop into the trash can. All right, here and here and here, stop. You see, and then on the right you see this is the motion diagram, but it just so, which means the X position, every Y position, every frame in the picture. So then you're done. You return this to, so that when this pop up, so you're done with the motion diagram. That's the first step. motion diagram is in a real space. So x position, y space, this simulates how the object actually drops. It's getting faster and faster, going like this. Now, the second step is graph y versus time. Produce a graph representing this. All right, produce a graph. Actually, data is already recorded in this. So all we have to do is to create and number 3, produce a graph and then create a table for the data. So the data is already kept. So this one is motion diagram. So then we click this thing, and we can even delete this. Okay, and so that one is the motion diagram, x versus 1. And then important here is you go here using these 3 dots, then all the 2 will pop up. You see that? The 2 pop up. And then you will do a graph. Click the graph, or drag to the page, or double click it. Okay, or drag to the page. So that's still my motion diagram over here. Alright, that's still my motion diagram. But then on this one, this is a new graph. See, on the left, it has selected vertical, but this is all for you to select. This is just like a graph paper. Alright, so then you choose object 1, the y coordinates in meters, and horizontal obviously in meter. So then this is the graph. So you just need to understand this graph. You can change the scale of this by doing this one, and I show you left click and change the properties, change the scale. But we probably don't change the scale. Change the scale so that the graph will cover most part of the frame. So then you can simply click this called auto fit, which means all of these are useless. See, the whole thing just happened between 0.6 and about 1 second. That just dropped very fast. It's only here. Therefore, you say well, auto fit, so they will blow up. So that's basically position versus time. So y position versus time. And so it's a parabola, upside down parabola. Is think about it, it's getting faster. If it's constant, it should go straight line like this, but not. Instead, it's going like this. So therefore, it is a parabola. So you're done for this graph. Okay, so then that's the equation. Okay, so that's and then we leave this here for now and see what we want to do. And we want also a table for this. So that's a table. So we have 4 ways to represent the function. That's the graphic. So now create a table for y of t using the table 2. So where's the table 2? Table 2 is the second thing over here. So then that's a table. You can double click. So there's a table. So of course we want a table for this one. Okay, and then you can put a title. You will say y over t and y of t. So therefore you will have here select the time. Usually that's in your way. That's the time, and then select the y object. So then boom. So this is the time. No, you don't want a date and time. So they can date it. I just simply use the time. So time is the video. Okay, this is a very interesting tool. So which is a 0.6 video, very fast. The object is at 1.9 meters. Basically, it's this guy, this person, Terran, is 1.9 meters above this tall. And then after 1 frame, 0.033 seconds, he is dropped to 0.1.7. And so this time, every time is like 1/30th of the second. And then the object keeps dropping. But if you do the math, it's getting faster and faster, or the distance gets lower and lower and lower based on the coordinate chosen. So you're done with this. So it is just examining this. So now, we don't need that big. So that's this, and so this is initial versus time. So there's one here. That's the position and velocity, position and the table. Now we want, what do we want next? Okay, we want, no, that's not this one. We want the velocity, y velocity versus time. So then what we actually do is using get y velocity and y, create a table. But this time, the same object, we want its velocity, which means the slope or the rate of change of this one. So get another one. So here is a new graph. So you can organize this to different locations. In fact, I think it will be very good. So move this over here. So it means that is the position, that's its table, then the velocity. I would say y velocity, choose y velocity, and then versus time. So then time will be this. So y velocity is the coordinates. We're free to choose coordinates because we're choosing going up as the positive. Therefore, all the velocity will be negative number, which is fine. But then the negative is basically the linearly going down, gets faster and faster. So it's always getting faster and faster. So this is the velocity. So this is done. Okay, and you can move this when it turns into a little hand. Move to here, and I probably don't need this one. I'll move this one here. Okay, and that's the motion diagram just below the picture. So that's the motion diagram. And this is y velocity. And one, and moving up over here. Velocity is negative, it's going down, so like this. So now, so then what's next? What do we want? I want create a table, okay, for the y velocity. Basically, it's a table going down. So a table of y velocity. Okay, and that one. So time and y velocity over here. So that's a table. It's all negative, and so that's this. Okay, and so follow the procedure. So just understand. You'll get some question about this in a test or exam. So y velocity going straight down because it gets larger and larger, gets faster and faster, but it's negative, stronger and stronger. So the table. So you will say, well, this is velocity y as function of t. It's negative. Okay, so it's all downward. Okay, so it's negative. So it's negative. So now what's next? All right, and then okay, equation perform a quadratic fit for this. Okay, note the a, b, c value. To make a note of the value. So this is actually a key point on this. We go back to the position versus time function. We already have this one is one. So now here is what we want to fit. So we want to fit with a quadratic formula here. All right, fit. And then we see here it's easily come out. We move this to this here. So it says I have A, B, and C. So then we have this. Okay, make a note of this. So that's all. So then we compare and the equation. So A is the acceleration divided by 2. So acceleration is 2 times of this, and the initial velocity is this, and 0.6, and initial position is positive 5. All right, plus or minus. So that's the initial velocity. But the way all we need to do is to get the acceleration. So now we have the fit pretty well. So then there will be a curve. So you see the line is the curve. So the quadratic curve fit perfectly with the line. Okay, so that's good. So that's the fit. Okay, insert a text box for calculated analysis. If the button is at the bottom on the right window. So so this software, you can use this for any work. So and you can turn in this, but in this case, I just want you to make a snapshot of this. But then you can enter a text box over here. Okay, enter a text box over here, text box to see here, text box. Text entry box. So this you can simply do your report. So the acceleration. So you can just copy down. A equals negative 6.68, and B equals 6.28, and C equals 0.5. So, and then, so acceleration, so calculated acceleration, see, as we say in the lab, is G equals, in this case, 2 times, I use X for the multiplication, okay? So hopefully you don't mind. So 2 times, so that one, negative 6.68, because I did approximately calculation, so that is, so what is the number? So the number is 6.68 times 2, so 13.36, so negative, okay, 13.36. Okay, so that's inaccuracy is not quite compared to, well, as compared to expected. Okay, 9.8, negative 9.8 meter per second square. I got 13 meter per second. 13 meter per second square. So you do something here. I don't want to use too much of the video time because the video file is big. So that's also the same units. 13 meter second. So 2. All right. Next, what we're going to do is going to calculate G again from the slope, from the velocity plot. Okay, you need to do a linear fit over here. So I actually already did it. So from here, you do a linear fit. So you're doing a linear fit, okay, here. And then with the M come out from the fit, it will be the slope. Now, obviously, it's 13.4, see, compared to here, 34. So then you type in the text box. So linear fit looks like it's perfect. So you will say, well, from the velocity Vy versus t, and then this, and then you will have slope. Okay, slope, and M equals negative 13.4. Okay, so that's the meter per second square. So that's the acceleration. Because this is an approximate calculation because I didn't really mean to be very accurate. I just quickly asked Terran to help me doing that. The error probably due to the scale. I didn't measure this, or probably the camera is too close. So because the scale is not exactly, but it's comparable from this slope. Therefore, the slope is simply so G here is equal to the slope, so that's as defined, okay, and negative 13. Negative 13.4 meter per second. All right, so then that's this, how calculate G, and then what else? Then compare to G value and comment on your result, because this is my result. I will comment my is at least in the same magnitude as expected G. Okay, normally people measure, they will get a 9.8, but I get a 13.4. Probably the size be too big or too small, and then I just illustrate the idea. And you use yours. Don't copy this number because you have your own video. Okay, once you're done, okay, and once you're done, and you don't, you probably enter it here. You don't need to do here, and then make a copy of what you have like this, and make a snapshot. So for example, you know, do the snapshot if it's on a window or on of the whole screen. Let me do this. Just pretend I'm a student. I will do this. Okay, and I will make a snapshot. So make a snapshot of the window. So here you go. So that's what we did. Yours. I expect you do all this with your own video, and that's pretty easy. And hopefully you understand every step. And then you paste into here. Snapshot, and then you go here and boom, that's the new one. Okay, I paste into here, so I don't want to replace that, but then replace that and then submit, and then you're perfect. All right, if you have any more questions, we can also make an appointment and meet in person in the lab or online. Bye bye for now.